And our next speaker is Stefan Truppe, who's going to tell us about laser cooling AlF.
Thanks, Lawrence. Thanks, Michael. Thanks, Simon, for organizing this wonderful conference. Today, I'm going to show you our recent progress in cooling AlF molecules. So again, a fluoride, but maybe slightly different. And so first, I just want to highlight that I'm now part of the Center for Cold Matter at Imperial. And this is a very highly collaborative environment where we do laser-cooled molecules for all kinds of different applications with atom interferometers, and now recently also electrons in penning traps to look for dark matter. What kind of molecules are we interested in cooling? So calcium fluoride has been around for a long time. I worked a lot on calcium fluoride during my postdoc. Then YBF to search for electron EDMs, new physics beyond the standard model. And now I developed this new kind of platform of AlF molecules to study bulk effects for quantum simulation, but also to study direct laser cooling to BEC or even evaporative cooling without shielding. And a very new project now together with the group in Dortmund is to actually also laser cool NH molecules. So hopefully by when I will retire, I will have laser cool a singlet, a doublet, and a triplet molecule. So that's my kind of goal. The AlF projects actually started at the Fritz Haber Institute in Berlin, where about 8 years ago, and it's still a very fruitful collaboration. So now, about 3 years ago, I moved to Imperial and set up kind of the second generation experiment. So over the time, we built quite a few machines. So we started with a supersonic beam machine to do spectroscopy in Berlin, and then very quickly cryogenic helium buffer gas machines to then study optical cycling, mod development, but also put a lot of effort into source development and slowing. And now at Imperial, we actually developed the generation 2 mod apparatus, try to implement Zeeman slowing and cooling, but also we have a dedicated effort to do laser development, especially in this deep ultraviolet range. So molecular mods, the status quo now is, okay, it started all with strontium fluoride, Yale, moved to Chicago, now to Johns Hopkins. Then we kind of, sorry, a bit off. We started this, made the first mod of calcium fluoride at Imperial, and that has really taken off now. And I think Lawrence already told me there's even like 2 more groups, so we'll have soon 11 experiments doing calcium fluoride molecules. We've got calcium OH and SROH at Harvard and YO at Gila. And very recently also the first barium fluoride mod at Zhejiang University. Hopefully we'll see calcium hydride, magnesium fluoride and YBF, NH and maybe even CH soon. What kind of properties do these mods actually have? So we see the number compared to like atomic mods is still relatively low. The density, we made very good progress. So we started with very, very low densities for retituned mods, but then also the Imperial group showed that you can do this beautiful blue detuned mods, first demonstrated in rubidium and then in Lawrence's group, and reach 10 to the 10 per cubic centimeter, even though the number is so low. Temperatures, we made very good progress here by cooling molecules already to a few microkelvin, reaching phase-space densities now on the order of 10 to the minus 6. So this is about 10 orders of magnitude in phase-space density in about 15 years. So I think it's quite a remarkable progress. When I started a new project at the Fritz, I really wanted to increase the number of molecules to push this up maybe to 10 to the 6 or 10 to the 7 in a dipole trap. And I really thought hard about how I would do that. So what limits this number actually in molecular mods? So first of all, we need to produce, First of all, we need to produce the molecules, so it's an inefficient source compared to an atomic source. So there's some chemistry involved. Until now, they were all radicals, so they have unpaired spins, so they react in the source, and they actually produce other species that are not necessarily calcium fluoride, for example, but we predominantly produce CaF2 in the source. They're pulsed, so there's a limited number per shot. There's typically a very long slowing distance that, again, incurs very large losses. There's no easy way to implement a Zeeman slower in these doublet molecules, and the capture velocity of the mods is usually quite low, with about 10 meters per second. So I thought, why not be inspired by history and find a kind of alkaline earth equivalent. And then when you look at the periodic table, there are a few species, And then I found this AlF as a very good candidate. So it's turns out we have a highly efficient source that produces AlF only. It's a closed shell, so all the reactions are endothermic. So it's quite a nice starting point. We can even make a CW source, or kind of a dispenser type source of these AlF molecules. It has a ginormous scattering force because it has a very large natural line width. And we can easily implement a transverse field, the Zeeman's law, to allow trap accumulation as well. Because of the large scattering force, it also has a high capture velocity. So I thought this is a kind of nice starting point to really explore if we can actually load, on the order of 10 to the 6 to 10 to the 7 into a high number and a high density in an ODT. The general strategy follows basically we start with a pulsed buffer gas beam that the molecules that we create are usually on the order of 3 to 5,000 Kelvin. We cool them with this cryogenic helium that flows through our cell, and then we just apply some radiation pressure slowing. And until now, all the molecular mods are loaded basically by chirped frequency laser slowing. So this is a pulse source. So everything here is pulsed, and so we load a single pulse of these molecules into our mod, and then we can apply subdoppler cooling and then load them into dipole traps and lattice. So now for AlF, is maybe a slightly different cooling scheme here. So it's a very simple molecule where you can just see what on this, for example, all Q lines are rotationally closed. So when we excite, for example, here on this Q1 line, we go up here to this J'1 on this to this blue line, and it can only decay back to this red line. So you can do the same on the Q2 line, Q3, Q10, and so on. One thing I want to highlight here is that the ground state G factor here is 0 and the excite state G factor is 1. So keep that in mind, because for all the molecules that have been cooled so far, the ground state G factor is about 1 and the excite state G factor is 0. And that's why this implementation of a Zeeman's law is not as straightforward. These molecules also only have one transition that's rotationally closed. And you see the ground state here is split, so there's some spin rotation structure you need to take care of. So this looks a bit simpler and gives you more flexibility, and the fact that we have the excite state G factor allows us to implement the Zeeman's law relatively straightforwardly. Both are type 2 transitions, so that means we have polarization dark states, which leads to subdoppler heating in a ready tuned mod, and that's why these molecular mods are typically quite hot and quite large. So if we actually compare AlF now to strontium, or our favorite kind of dummy atom is cadmium here, then you really see how this resembles an alkaline earth atom. So you have this really strong 1s to 1p transition in cadmium here. The same is true here for AlF at 227.5 nanometers, 84 megahertz wide. And cadmium is 228.9 nanometer and 100 megahertz. And the same way as strontium or cadmium, we have also this triplet P012, and here in the molecule it's called a triplet pi 0, 1, and 2. And obviously there was not that much known about this molecule, so we had to do a lot of spectroscopy, specifically figuring out how large this inter-system crossing leakage is from the singlet pi to the triplet pi. Because if this leakage is a bit too large, then we would need about 6 to 8 more repumps, which would make it not feasible. Apart from that, you also see that we have this nice spin forbidden transition here at 367 nanometers, which we want to use for narrow line cooling. It's slightly on the narrow side with 85 hertz to the triplet pi 1. So we actually need to implement some quenching. So we couple this state to the asinglet pi state to tune the lifetime of this triplet pi state. Some of you might have spotted that the maybe slight disadvantage here is that the deep UV wavelength at 228 to 2 to 7.5 nanometers. So it actually required a really dedicated, very long-term effort to develop laser systems as well. So it has excellent Franconia factors. So you can see we can scatter 200 photons with only one laser and about 10 to the 5 photons with 3 lasers. It has very strong optical transition, so we expect a very large capture velocity of about 50 meters per second. And if we can manage to get this spin forbidden transition broad enough for narrow line cooling to be efficient, we can cool them easily to 3 microkelvin. And like I said, the cooling scheme allows a transverse field semi-slow, and then we can actually do trap accumulation as well. So we get rid of this single pulse loading, but we can actually now load many pulses. The nice feature about this triplet pi state is that it's a really new resource. We can excite the molecules to these triplet pi states. They're very long-lived states with very small lambda doublets, and then we can polarize the molecule with even just 100 volts per centimeter. We can toggle on and off the magnetic moment if we want to for quantum simulation applications, and we can even cycle molecules here, transfer them into this triplet pi state where they're magnetically trapped. And then after about a few milliseconds, they will decay back down and rejoin this optical cycling. So we don't even need to close it on such a high level because we can use this triplet state as a new kind of resource. So obviously it's never that easy. There is, like Tim said, there's quite a bit of hyperfine structure usually involved. So the aluminum nucleus has a spin of 5 halves, and the fluorine has a spin of 1 half. So each of these J, for example, this J equals 1 state is now split into 3 by the aluminum spin, and then each of these F1 levels is again split by the fluorine spin. But the fluorine interaction is quite small, and we can basically, it's negligible. Because our transition is so broad, the whole ground state structure is unresolved. So this is about 12 megahertz, whereas our line width is 84 megahertz. In the excited state, we get the same structure. Everything is just about 30 times larger. And we see that it's partially resolved, and I plotted here the natural line width. So with a bit of power broadening, we can actually couple all these states back into our optical cycle. What does a kind of spectrum look like here? Here you can really see that for higher Q lines, so here we see this partially resolved hyperfine structure on the Q1 line. Then when we go to higher Q lines, the hyperfine structure tends to collapse and narrow down. This is what I plot here. So blue and red are states of opposite parity. And that becomes important later when we talk about magneto-optical trapping. What happens here is that you have very closely spaced lambda doublets in this excited state. So very, very small stray electric fields can actually mix those together and break our rotational selection rule. So we have to be a bit more careful with electric fields in our Mott chamber. It's an extremely strongly bound molecule, and so it's also interesting from a perspective of collisions. Because there are no reactions are strongly endothermic, so there will be no reactions even at high density. AlF is light and small, so there's a really low density of states, and there are only weakly bound van der Waals dimers here. And I'm really happy that Michael and his team actually now calculate the potential energy surfaces for this. And you can see that it's extremely shallow, but it also means that excitation with an optical dipole trap is actually really unlikely because all the excited states are really far up. So that's a kind of promising thing. And now I'm just like also asking you in the audience, is it maybe it's possible to do evaporative cooling without shielding in this system? The strong bound also means that we have an extremely efficient source, so that we can, so that it's really difficult to make anything else than aluminum fluoride, which is very different to the other molecules. So we can make an oven, we can make a dispenser source, and the molecule is actually so robust that it will survive collisions with the chamber walls. And so that's really nice because now we can really think of loading a molecular mod from a dispenser type source, and we get rid of all this cryogenic business. So when we started, there was not much known, especially about the levels that are important for laser cooling. So for about 2 years, we just spent on spectroscopy to understand exactly, does the source work, what are the lifetimes of these triplet states, because these were unknown. What are the lifetimes actually of our laser cooling states that we need? What's the hyperfine structure? What is the dipole moment of the molecule? There were some preliminary measurements early on, but we wanted to know it more precisely. Most importantly, we had to measure electronic, vibrational, rotational branching in this molecule. Obviously, because you see the ionization potential is less than twice the photon energy, so 2-photon ionization becomes a problem. So we had to measure this as a new loss rate as well. Like I said, there's parity mixing in the excited state that we had to characterize and to understand fully this kind of polarization dark states. Is a Mott even possible in the system? When we started, we didn't know. And how can we actually come up with subdoppler narrow line cooling schemes? Because as you can expect, once we get a mod, it will be very hot. And what is a kind of a feasible accumulation scheme? So what you see here is our first attempt. Very early on, we excited the molecules actually straight to this triplet manifold, and then did selective, state selective ionization from there with different wavelengths via different intermediate states. And so this is a pulse dye laser broad spectrum. And then we zoom in here and then excite actually this spin forbidden transition here with a CW laser, and reveals really nicely this excited hyperfine structure. And then we can even drive microwave transitions in this triplet manifold between the opposite parity states and measure the lambda doubling with really high precision. So this is just one aspect. There's many other states that we had to characterize, but I want to move on and actually show you how easy it is to produce AlF compared to other molecules. So here in the same beam machine, I made a beam of magnesium fluoride, calcium fluoride, and YBF. And in the same kind of detector, you need to be careful to characterize them well. You see that the AlF is just at least an order of magnitude better. And we can even detect the aluminum atoms. And once we flow some Na3, you see that there's a big chunk of aluminum atoms that's gone, that's been now reacted to AlF. And then we can actually characterize this whole and predict how much AlF we expect, and it fits quite nicely to this kind of AlF beam brightness that we measure. So here just a quick mention that we also built kind of a first oven source that we now also want to investigate. And here you see that we can, in this kind of hot temperature oven, you see many rotational states being populated. But the great thing is that it's extremely intense. So this is our pulse ablation source here, and you see this kind of CW source from this oven is many orders of magnitude brighter. Now the question is just, can we cool those rotational states down so we can actually boost our low J signal even further? We are currently investigating that. And Pulkit and Priyanshi have a poster still up, so please talk to them. Here you see our first attempts in making a dispenser type source, and actually then measure Q branch spectrum as a kind of thermometer to see if they how well they thermalize with the chamber walls. So then we established a kind of our first optical cycle, and you see on the Q lines we really straight away saw a massive enhancement in our signal compared to the R line, which was a bit of a surprise in the beginning, but that we didn't need to modulate our polarization at all. But because of the hyperfine structure, it actually turns out that there's enough of a remixing of these dark MJ levels that we can just, with a single laser beam, few millimeters wide, immediately scatter around 200 photons. We can do optical pumping very easily to enhance our population in this J equals 1 state by about a factor 3 to 4. And then we tested also, can we pump the molecules into the first vibrational state and then pump them back? This is really essential that we understand this repumping mechanism to see if our laser cooling can actually work. So our strategy then was quite clear. We established this optical cycle. We understood all the leakage channels and all the possible decay channels that would make laser cooling impossible of this species. And then we just said, okay, let's follow a kind of a laser complexity roadmap. So first, like I showed you, we established an optical cycle. We understand it really well. So here you also see that we can model this interaction quite well using by solving optical Bloch equations. We also deflected the molecules to really understand what kind of accelerations we can impart. And then after this, we really started to develop the deep ultraviolet MOT apparatus. And first, we tested this by just loading a cadmium MOT from a vapor, where we only need one DUV laser. Then we loaded a cadmium MOT from a buffer gas beam, that allowed us to really study the slowing, loading the MOT from this buffer gas beam now with 2 DUV lasers. We can test the preliminary kind of Zeeman slower that was only, basically 2 fridge magnets about 1 centimeter long. And we could also test this accumulation scheme. So here I just show quickly that we can use cadmium, and especially the narrow lining cadmium, as a beautiful velocity probe to analyze our buffer gas beam. So this is basically we measure the arrival time and then measure the velocity first through the Doppler shift. And when we then apply a slowing beam, you can see we chirp it. We really see how a big fraction of the beam is now slowed to about 10, 20 meters per second. So this means now that we can chirp these complex laser systems, all the cavities stay locked. We can actually impart this really strong acceleration onto these cadmium atoms, and that at least for atoms that seem very promising. Then, oops, sorry. Then we loaded a cadmium MOT from this buffer gas beam with two DOV lasers, and it was really nice because this really was the first time that we could really show a very high loading rate, which led to a record density cadmium MOT. And then a very nice first feature that we applied to is to actually study this trap accumulation scheme, so we can really now increase the number of atoms, or then in the future molecules, in our trap. We studied the slowing very well, and here you can actually see them with 3 DOV lasers. We can now slow AlF molecules, and because of the excited state hyperfine structure, so here basically is the slowing force, the function of the velocity. So you can see that we have over 100 meters per second at quite decent slowing force, and that just comes from this large excited state hyperfine structure. So it's kind of a natural white light slower. And when we apply this to our molecules, then you can see we can now slow them down for about 150 meters per second to below 50 meters per second with a very gentle chirp at the end. But the big chunk is actually done by kind of a natural white light slower. So then once we figured out that the slowing can actually work, then we just had to add one more DOV laser, a fourth one, and then we could really look if we could load a magneto-optical trap. So now we needed 4 DOV lasers with 200 milliwatts each, and we also realized that we need quite a high magnetic field gradient of about 1,000 Gauss per centimeter. So for this, we started with a permanent magnet. So there's a ring permanent magnets in our MOT chamber here, and you can see we actually have to recycle our laser power here because the saturation intensity for AlF is watts per square centimeter. So we need a lot of power, and the easiest way we could think of was just to recycle the beams like this. So we split them into 2, a vertical beam and a horizontal beam, and then retroreflect it like so. The Q1 MOT has 72 levels, and the Q3 MOT is 168 levels involved. And if you include the repumps, then you end up with 420 levels. So it's quite a complicated MOT. And like I said, we need these very large magnetic field gradients. Then if you look at the actual Zeeman shifts and splittings in the excited state here for the J equals 1 in the excited state and J equals 3, you can see where we park now our laser to look for the MOT. So it's a normal kind of red detuned MOT, just with a bit more added complexity and a high magnetic field gradient. And this is what it looks like. So we start here with just a Q1 line just to see what the source looks like. Then we add the slowing beams. Then you see some extra structure here because of just the way we apply the slowing beam. And if we have the polarizations the wrong way around, you don't see any appreciable trapping here. But if you then switch the MOT to the right polarization around, then you see an extended kind of lifetime. Then if you actually take a picture and see if you can actually see any appreciable trapped molecule density, then you only see it for the right polarization that we expect for MOT to work. Then we can do this for the Q2 and the Q3 as well, and they all work. Now the biggest problem is just our lifetime is 10 milliseconds, which obviously even for molecular MOT standards is quite short. So we did some extensive simulations now to actually understand how this MOT works and what the temperature should be. So we're quite happy now that we can actually predict temperatures quite well, and also a strategy on how we can lower the temperature in these blue detuned MOTs to about 100 microkelvin in a few milliseconds. And you can see here that our MOT is so hot that actually if our gradient is too shallow, they will just boil off. And so we need an even higher gradient probably to make a deeper trap to contain our quite hot molecules. And just a quick outlook. So we need to now understand these losses a bit more. Is this just related to some patch potentials in our MOT chamber? Is it maybe we underestimated the 2-photon ionization cross section, and there's still a bit of a higher ionization loss channel? This is work this is work going on now. But the next thing is obviously decrease the temperature, increase the number, control the electric fields better, and then replace permanent with electromagnets. And on the way somewhere we tried dispenser loading. One thing I just wanted to highlight quickly is there's obviously a lot of DUV challenges involved in this project. So we have quadruple tight sapphire lasers. So for 4 lasers, we have 16 laser cavities, including the pump lasers that must stay locked and stable. And so that's when a big problem was also that we faced laser-induced damage in our vacuum viewports. So a dedicated new effort to really make robust, small, compact, and affordable DUV lasers now on the way. And I'm really happy that this is working out really well. We can now, with industry partners together, really tackle this kind of last frontier of DUV lasers to make them much more robust. So now we are already down to only 8 cavities. So we already cut the cavities by a factor 2. We don't have any pump lasers anymore. And we also now solve this long-standing issue of degradation of BBO crystals. And more importantly, we solved this issue of degrading vacuum viewports. So I think there's nothing else on the way anymore. I just want to highlight that now we produce typically on the order of 450 to 500 milliwatts of DUV light. And with these newly built laser systems that are compact and easy to operate, we can already, we did some first slowing experiments now to really show that these new laser systems can be robust enough for laser cooling experiments. So with this, I just want to conclude. I showed you that AlF is now one of the best characterized diatomics. So that's now also a subject of lots of quantum chemistry calculations to really kind of compare the calculations to our spectroscopic measurements. We made a record density cadmium MOT on the way just to test our system, and showed you that we now have the first MOT of a stable molecule, and it's also the shortest wavelength MOT so far. For the first time, we could trap not only at 1 rotational state, but now also up to j equals 3. And we now built a comprehensive kind of MOT simulator to simulate this very complex MOT that involves up to 400 levels. So this is kind of on the side, we have a very nice European effort now to make robust, compact, and affordable DUV lasers. So if anyone of you is interested to work in the UV at some point, just let me know. I think we're making really good progress now. All right, with that, I'm come to an end. I'll just say thank you for your attention, and I'm happy to answer any questions.
Questions? I have a quick question.
Yeah.
What's the dipole moment of the triplet pi state?
1.6 dBi.
Yes, I have a question about this continuous source that is potentially possible. How dirty is that compared to atomic ovens, or how dirty is it compared to a buffer gas beam where you can just block off the helium all the time? Is that something that is going to waste your vacuum in the end, or not?
No, at the moment we see that it's a high. We only produce AlF in the end, so it's actually quite surprising, right? So we literally wrap some AlF3 powder into some tin foil or aluminum foil, pop it in the oven, and only AlF comes out.
Questions? Right there.
Yeah, I'm just curious. So you mentioned that the G order is opposite, and that makes a difference. And could you briefly say why?
So if you have a ground state G factor like in calcium fluoride, then if you build a traditional Zeeman slower, you basically always optically pump very quickly into the states you don't want to pump to. Whereas if it's in the excited state, you can nicely select exactly the components that have the right Zeeman shift to compensate for your changing Doppler shift.
So the important thing is G of the excited state.
Yeah.
Okay.
All right, if there are no further questions, let's thank Stefan Truppe again.